In all the previous videos on chronoamperometry, we've been mostly focused on semi-infinite linear diffusion. And what that means is that if we have our electrode, all of our ions are diffusing straight perpendicular to our electrode surface. However, microelectrodes and roughness introduce some non-perpendicular flux. Let's take a look at what that means. Ultramicroelectrodes are electrodes that are really, really small, typically on the scale of 25 microns or smaller. And if you look, there's a bunch of different geometries. Here I have 4 different ones, but there's many others. These are the most common ones: spherical, hemispherical, disc, and cylindrical. From the top view, the spherical, hemispherical, and disc look pretty much the same. You have an electrode in the center, represented by the black, and then an insulator around it, represented by the blue or green color around it. But when you look at the side cross-sectional view, the differences between the spherical, hemispherical, and disc become readily apparent. The spherical is a full sphere with a tapered insulator around it. That way, the entirety of the sphere's surface is exposed as much as possible, so that you have true spherical behavior. The hemisphere is just half a sphere, which makes it a little bit easier to make because you don't need this tapered insulator, and you just have half the sphere and then a wire attached to that going through the insulator. The disc is embedded inside the insulator so that only the round face of it is exposed to the solution, and you have this disc. In each of these cases, we no longer have just semi-infinite linear diffusion. We have diffusion coming from further out in the solution, converging towards the electrode. This enhances the flux at the electrode surface because you have all of these flux lines coming together and converging near the surface. The spherical looks like what I just drew, and the disc, though, towards the middle, you have more semi-infinite linear diffusion behavior, but towards the edge, you have flux coming in from the side at an angle or even straight on. So you have an enhanced flux on the edges, and towards the center, it's closer to semi-infinite linear diffusion. Either way, the entire disk experiences an enhanced flux greater than what would occur with semi-infinite linear diffusion. The cylindrical electrode is a long, very skinny wire, and this enhances the flux because all around the side, you have these flux lines that all converge, creating a higher flux than if you would have at a flat plate, where you'd have more semi-infinite linear diffusion. You can see how as these arrows come towards the cylinder or towards the sphere, they come closer and closer together, and so the flux increases as you come closer to that surface. These are the typical relationships for ultramicroelectrodes. For the sphere, the math's been worked out. You have this transient response at short times, and then at long times, you get this steady state response. Notice how this equation is completely independent of time. The disk, it has the relationship of the Cottrell equation at short times. At intermediate times, it's some sort of mixed, and it's a bit more messy, so I don't have it displayed here. And then also at longer times, you eventually get to this steady state behavior here that looks very similar to the spherical, slightly different though. The cylindrical electrode, it has this expression here at transient times, but its steady state response isn't truly steady state. It's more quasi. You can see how there's still a weak time dependence there. So we'll call this a quasi steady state relationship. And what's really nice about these steady state responses is that you don't have the additional variable of time involved. Now, what are some of the benefits and drawbacks of using a microelectrode? Well, first, the benefits is you get these steady state currents due to the fast mass transport. You minimize capacitive effects because you have that smaller surface area. And because you have that smaller surface area, you have very low currents, meaning you have very little ohmic drop, and you have high spatial resolution. What that means is I can move my microelectrode within my system to detect any potential differences in composition or behavior. This is really helpful for biological systems, so you can probe tissues and things like that. And then with the microelectrodes, you can do very fast scan rates. You can study things that are very fast reactions that occur. And that's because of these low currents. You can go to higher scan rates. Now, the drawback is because you have these smaller currents, you're more susceptible to noise. Your signal to noise ratio is a lot lower. That means you've got to go to elaborate lengths to reduce any stray vibrations, electromagnetic fields that may disrupt your current in your electrochemical cell. They're also challenging to make. You can buy microelectrodes off the shelf for aqueous systems, but in molten salts, there is no such thing. And in most systems, the insulator and the metal and the molten salt are not compatible. A couple people have tried to build microelectrodes and use them in molten salts, but the insulator has delaminated from the electrode. This is yet to be successfully employed regularly in molten salts because of material incompatibility. It's also sensitive to convection and surface chemistry and surface defects. Talking about surface defects, one defect could be the roughness. You want to make sure you have very smooth electrodes if you're going to have a microelectrode. And even with macroelectrodes, this can be important, especially at short timescales. Ideally, you have a perfectly smooth electrode like this one on the left here. And when that's the case, you can get that semi-infinite linear diffusion at a macroelectrode, and all of the ions arrive about the same time and completely aligned with each other. You don't have any ions coming in at different angles. But when you have a rough electrode with a thin diffusion layer, this is like at short times, you have these hills and valleys, and at these points, you can see that we have arrows sort of condensing closer together. We have this enhanced flux at the points, and then down in the valleys, we have much lower flux. At these short times, you're not really getting semi-infinite linear diffusion. In some spots, you're getting maybe radial diffusion or spherical diffusion. And at some spots, you may be getting very little, almost no flux coming to the surface. However, as that diffusion layer thickens, that rough surface begins to look more smooth to the ions as they diffuse from further out, and it becomes less significant. All right, that's microelectrodes and surface roughness. Join us for the next video where we're going to be looking at multiple species and chronoamperometry.